All right, welcome to lesson number 6. This lesson is more or less the same as lesson number 5. So we're still dealing with stretches about the x or y axis. Now, just a quick little review. Remember, if we're talking about stretches about the x or y axis, what it means is we're either moving. So if I were to stretch this parabola about the x-axis, that means I'm moving or to, away or towards my x-axis. If it's a stretch about the y-axis, I'm moving away or towards my y-axis. All right, so let's look at this first example where we need to write the equation of the image of y equals x squared after we perform a horizontal stretch about the y-axis by a factor of 3/4. So if we're doing a horizontal stretch about the y-axis, that means it's moving about our y-axis, which means our x values are going to be changing because it's moving closer or further away from our y-axis. So if it's a factor of 3/4, then we're going to flip this, and that's going to become 4/3 x. And so if I were to rewrite this as an equation, we're going to be left with y is equal to 4/3 x, because that's going to be substituted for my x value. And if I expand this, we're going to be left with y is equal to 16/9 x squared. All right, so if I have the equation y equals the square root of x minus 3, and I perform a horizontal stretch by a factor of 4, and that's about the y-axis, and a vertical stretch by a factor of 2 about the x-axis, the first thing I'm doing is if I have a factor of 4 about the y-axis, that means my value of x's are going to be mapped to 1/4 x, factor of 4. And my values of y are going to be mapped 1/2 y. And so as an equation, this is going to look like 1/2 y is equal to the square root of 1/4 x minus 3. Now, if I want to get this out of this form here, then what I can, and sorry, this should not be under the square root. That's square root of 1/4 x minus 3. Now what I want to do is I want to bring my 1/2 to the other side. So I'll multiply both sides by 2, which will leave me with 1/4 x minus 6, because I multiplied both those by 2. All right, so I can leave it like this, or I can leave it like this, or I can get rid of this square root here. And to get rid of the square root, I'm just going to expand this. 1/4 x is going to be the same thing as 1/2 x. And so y is going to equal 2 times 1/2 square root of x minus 6. Now, if I want to get rid of this 2 and this 1/2, I'll just multiply those together. I'm factoring that, or I'm multiplying that into my brackets, so that's going to leave me with 1 on the inside. 2 times 1/2 is 1. And we get the square root of x minus 6. Okay, so this one you can probably do yourself. All we're doing is we're mapping our y values by a factor of 1/3. So my y values are going to be 3y. And we're also having a reflection, so my y's are also being reflected to negative y. If we combine those two parameters, I'm going to be left with y. Those two transformations, y will be mapped to negative 3y. And just add that into the equation and you'll be able to solve for y. All right, we'll do a couple of these. I'm not going to do all of these. I'll just do a few. So what we need to do is describe how the graph of the second function compares to the graph of the first function. So if I'm looking at my x values were mapped to 1/2 x. So this would be a horizontal stretch. We know that because it's evaluating x. A horizontal stretch by a factor of 2. And that's the y-axis. All right, so let's look at, and again, I'm just going to write what's going on with our mapping here. So here we mapped to 3x. Here we actually, let's see what we did here. So we mapped our y values. And so our y value got mapped to 1/2 y. And so if I'm talking about something that's being mapped on my y value, then that's going to be a vertical stretch. Vertical stretch by a factor of 2. This is 1/2 y, factor of 2, and that's about the x-axis. And that looks like it's negative 1/2, which I didn't catch the first time, negative 1/2, so there's also a reflection. Plus a reflection in the x-axis. All right, now let's do the ones with an absolute value. Here, if I look at this one here, there's two transformations being performed. There's a vertical stretch, or no, sorry, just one transformation. There's a vertical stretch by a factor of 1/3. And yeah, so that's going to be about the x-axis. Here I have two transformations taking place, as I do here. All right, so in this first one, I have a horizontal stretch by a factor of 3, and I also have a vertical stretch, and this vertical stretch is going to be a factor of 1/2. Or sorry, a factor of 2, so it'll be 1/2 my y values. Now let's look at the absolute value function over here. So if I look at my values of x, don't let these absolute values intimidate you, but my value of x was mapped to 2x, but I also have a reflection occurring here, which would be negative x. And if I combine those two transformations, then my values of x are being mapped to negative 2x. And so this is going to become a horizontal stretch. A horizontal stretch, and this is by a factor of 1/2, and both of these are occurring about the y-axis, and a reflection in the y-axis. Okay, let's look at the next examples where we have our functions represented by thick lines, and we need to write an equation for each function represented by the thick line. All right, so this is the function that we need to write about. So it looks like what I have here is a vertical stretch taking place. And so if I look at my initial value, which was at 6, and my new value, which is at 2, I have a vertical stretch taking place. And since I shrunk from 6 to 2, I have compression taking place, then this is going to be decreasing by a factor of 1/2. And so I have a vertical, and remember we call them all stretches, so a vertical stretch by a factor of 1/2 about the x-axis. So it's getting closer to my x-axis. Now, if I were to write this as an equation, it's my y values that are actually stretching, so that my y would go to 2y. And so if I bring this to the other side, 2y is equal to 6 over x squared plus 1. And if I isolate that y is going to equal 1/2 6 times x squared plus 1. And I can leave it like this, or I can expand this as a function. And if I were to expand this, I'm going to be left with y is equal to 6 over 2x squared plus 2, and that if I factor the 2's out of here and out of here, then I'm left with 3 over x squared plus 1. And let's look at this one next. So if I'm looking at my values of x here, I have a horizontal stretch taking place. So if I look at this function, it's been stretched out like this. So they're moving further away from my y-axis. So I have a horizontal stretch. And it looks like by a factor of, well, if I move from here, 1, 2, let's look at our lines here. So I'm at 4 and I go to 8, so that's by a factor of 2. Horizontal stretch by a factor of 2 about the y-axis. And so again, I was at -4 and I stretched this, so now my x-intercept is going to be not at -4 anymore, but it's going to be at 5, 6, 7, 8 at -8. And when I was at 2, I ended up at 4, so my x values are increasing by 2. So x is going to move to 1/2 x. And if I input this into my equation, which is here, y is equal to 1/2 x plus 4 times 1/2 x minus 2 times 1/2 x minus 6. If I factor out the 1/2, divide both these by 1/2, I'll be left with 1/2 x plus 8 times 1/2 x minus 4 times, bring out that 1/2 x minus 3. And if I combine this, I'll be left 1/2 times 1/2 times 1/2. It's going to be 1/8 x plus 8 x minus 4 x minus 3. And our last example, we only really need to look at one of them. So a polynomial function has the equation p of x is equal to x minus 4 times x plus 3 times x plus 6. What we want to do is determine the zeros and the y-intercept if the following transformations are applied. So if I have -3p, then what this means is if I bring that -3 to the other side, I would have 1/3 y. And so if I were to plug this into my equation, it's going to be -1/3 y is equal to p of x. Into my equation, the zeros of px, if I have x minus 4, p of x is equal to x minus 4 times x plus 3 times x plus 6. Remember, the zeros, and this is going to be a linear, or not linear, cubic function, but the zeros are, if we set each of these individual function, or not functions, but factors equal to 0 and solve for x, I'm going to get my x values, my zeros, which are equal to 4, -3, and -6. Okay, so I've determined the zeros, but I haven't determined the y-intercept if this following transformation is applied. And so in order to find that y-intercept, I'm going to have to actually apply this transformation. So my y is going to be mapped to -1/3 y, which means that's going to be a vertical stretch. A vertical stretch by a factor of 3, and that's going to be about the x-axis. And if I look at the reflection here. That's negative, so there's also going to be a reflection and a reflection in the x-axis. So there's not going to be any change to the zeros, but there will be a change to my y-intercept. So let's see what this function is going to look like. So if I have x minus 4, x plus 3, and x plus 6. Alright, so here's my x-intercept at positive 4, my x-intercept at negative 3, and my x-intercept at negative 6. Now, if I want to find my y-intercept, I'm going to have to zoom out here. I'm just going to have to zoom way out. In fact, let's change our window settings here so that my y min goes to negative 100, and my y max we can leave at like 2, doesn't really matter. Alright, so here's where we cross our y axis, and so we'll trace, find our intersection point, and we are at negative 72. So that's with our original graph. So let's see what will happen if we apply a change in our function here. So if I change this by multiplying it by negative 3, so my original y-intercept was negative 72, and if I apply a vertical stretch by a factor of 3, but if I also reflect it, I multiply it by negative 3, this is going to multiply to give me positive 216. And so our zeros are going to be 4, negative 3, and negative 6. And my y-intercept is going to be at 216.